Hello, Mr. Ryan, are you right?
Yes.
Okay, so we have been talking about this problem for like 2 days. Yeah. So the problem is that we are given an undirected graph. We want to count how many unreachable pairs in this undirected graph, right? And we talk about the depth of search. We talk about the breadth of search. The key point here is to compute the number of the vertex in this connected component. If we do this depth of search or breadth of search of this connected component, if we find out the number of vertex is C, there are total n vertex. So the number of vertex that are not in this connected component is n minus C. Okay? So if we keep doing that, we sum up C times n minus C, right? Then we need to divide it by 2. That's the total number of the unreachable pairs. So depth of search, breadth of search just differs the way, the order, the traversal, the vertex in the graph, in the undirected graph. And for all the vertex in the same component, connected component, we only added the contribution C times n minus C once, right? So we use the hash set to remember the vertex that have been visited. This is depth of search, recursion, yeah? Breadth of search using the Q, okay? And the key point here is C equals depth of search of breadth of C, and answer plus equals C times n minus C, and at the end we need to return answer divided by 2. Because look, if we are looking at this vertex here, we form the pairs, unreachable pairs to for example like this vertex. When we traverse the component, right, you will form unreachable pair to the one we already calculated, so we need to divide it by 2. Okay? We learned about this formula. The number of edges equals to the sum of the degree for all the vertex divided by 2. Right? Remember, the number of edges equals the sum of all the vertex degree divided by 2. Then I belongs to the vertex. Okay? Yeah? Look at this undirected graph. How many edges? 1, 2, 3. We sum the degree, right? 1 plus 2 plus 2 plus 1 divided by 2. We need to divide it by 2 because one edge contributes to the degree of 2 because the edge has 2 endpoints, right? And for the undirected graph, the degree of the vertex is just the number of edges connected to it. And for a directed graph, the number of the vertex can be divided by 2 counts, right? One is the incoming, the other one is the outgoing. So the degree is the sum of both incoming and outgoing edges. Okay, so now we want to talk about solving this problem using a union find, disjoint set, right? Yeah? Remember we talked about the disjoint set. Disjoint set. So there are n vertex, for example there are 4, right? Let's just do this. 0, 1, 2, 3. Okay. So how many unreachable pairs here?
4.
4. 2 times 2, right? So if we use depth of search and breadth of search, we do this. 2 times 4 minus 2 plus 2 times 4 minus 2 divided by 2, right? We need to sum up the contribution and then divide by 2. For example, this 0, 1, 2, 3. 0, 1, 2, 3. Okay, so there are 4 vertex. 0 to 1. So 0 and 1 it belongs to the same group, right? So we add the edge. 3 and 2, okay, 2. So there are 2 groups now, 2 groups. Then we just have to go through, we use the union find, we go through these and then we find out the number of the size of it, right? Yeah, the size of it. So that's 2, and then we do the same. Let's say union find equals disjoint set, okay? And there are n vertex. Yeah, we're going to implement this later, okay? And then for A, B in edges, then we do this UF dot merge, okay? Merge A and B. So it means that we want to make A and B belongs to the same group, okay? And then answer equals 0. Then for go through the vertex range N. C equals, we want to get the size. Get the size, you have to get size I, then answer plus equals C times n minus C, return answer divided by 2, okay? Shift it to the right, one position to the right, that's the same as divided by 2. Simple, right? So the key thing here is disjoint set. We implement this before, right? Disjoint set. And we talk about, remember, we talk about merging. So which one is better? Is it better if we merge, put these all things, put all the vertex of bigger size into a smaller one, or put a smaller group into the big one? Remember we talked about it. Why is better?
Because it's less confusing.
It's less confusing. Yes, you're right. Yes. So look, if we want to compress, we want to minimize the total number of the paths, right? So the disjoint set, we have this operation of to compress the paths. If we want to merge two components, we prefer putting the group of smaller size into a bigger one. We also have to add in the get size. Okay? The get size function, we can keep tracking of the size of the components when we do this merge. Okay.
Whoopsie daisies.
Define. Actually, that's a class. Okay. Class. Disjoint set. That's an object. Define in initialization, that's a constructor self and n. Then we want to give a self.n is the n. That's the number of the vertex, number of the initial groups. Self.parent, parent at the beginning is list range n. Okay. So at the beginning, each vertex belongs to is a group of itself. Okay, so the group will be 0, 1, 2, up to n. And then we have a size. Okay. The size will be all 1, right? At the beginning, each vertex is a group of 1. This is to find the parent of a group X. We want to find the parent of X. We can do this iteratively or recursion, right? Look, if x not equal self.parent x, then self.parent x equals find self.find x, okay? And then return self.parent. This is the easiest way. So here, this is to compress the path. If this number is not equals to it's not a top element, right? Because at the beginning, the vertex 0 belongs to the group 0. The vertex 1 belongs to the group 1. So if this is not a top element, then we keep tracking until we find it. So, but we also need to compress the path. This define is to compress the path, okay? And we can do this iteratively as well. So by doing it iteratively, first of all, we need to find the root, right? So why x not equals to self.parent x, then x equals self.parent x. Then we have this parent x, which is the root. We can go through these paths again and then compress by reassigning the paths. So look, we have a group of these. We want to find these, the parent of this one. So the parent of this one is this. So what does it become? So that's 0, 1, 2, 3. So look at the 3, the parent of 3 is 0, right? So at the end, the 0, and then the 3, right? The 2's parent is 0 as well. So here, the 1 the parent here, okay? This is inefficient. It's like a linked list. In the worst case, it's O n linear time to traverse, right? To find it. So we want this kind of structure to make it like O1 constant time.
Yes.
Yeah? So that's why we need to compress the path this way. Okay. So this is to find the parent. When we find the parent, we do this compression of the path. Merge. We want to merge two groups, x, y. Okay. So look, first of all, we need to find the group A and B equals self-define x, self-define y. Right? If A and B, if they already belongs to the same group, we just return false, right? There's no point to merge them if they already belongs to the same group. If they are not in the same group, then we have to check the sizes. If self.size x is smaller than self.size y, then we can swap xy equals yx. So basically self.size x X is now bigger. Right? Then we want to merge the group of smaller one into the bigger one. Okay? This is A and B. Yeah. A, if we want to check the size, AB equals BA. And then self.parent B equals A. Right? Now A is bigger, so we want to move the B to A. Right? Make the group of B A. Self.size A plus equals self.size B. So look, this is A. This is B, right? We want to merge B into A. So what happened? The size of A needs to be incremented by size of B. That's what it means. Here, right? And size of B, because we want to have another function defined, size, get size, right? We want to use this function, get size. Then we have to reset size B equals 0. Okay? And then return true. Get size, return just self.size X. Okay? So this is the disjoint set. And we can use the disjoint set to perform union find. Right? Union find. So at the beginning, there are n vertices. So there are n groups. Right? And if we go through the edges, for example, if there is edges A1 to 2, we merge vertex 1 to merge 2. Right? And then we have a getSize function to return the number of vertex in the group. For example, if it's C, then reachable pairs will be C times n minus C. That part is the same. If we merge two groups, then the total number of groups minus equals 1, right? And another function is to check if two connected. If two connected, we just have to find, look, connected x, y. We just have to check if self-defined x equals self-defined y. We just have to find the parents, right? If the parents are the same, then they belong to the same group, okay? What's the problem and what have you learned today? What's the approach we are taking to solve this problem?
The problem is we have these
graph undirected ones.
Yeah, we have this undirected graph and
the unreachable thing.
unreachable pair. Okay, let me do this. Okay, 0. Okay, so we don't need actually the number. So how many unreachable pairs?
So we
How many top vertex?
7.
7 vertex, n equals 7. Okay, so how do we get the number of the unreachable pairs? 2 times 7 minus 2 plus 3 times 7 minus 3 plus 2 times 7 minus 2. Can you tell me what's this? Why do we need to subtract? 2 vertex? So how many unreachable pairs can we form? We can form unreachable pairs from the vertex here to all the vertex other than these 2 vertex, am I right? So that's 2 times 7 minus 2. 7 minus 2 means there are 5 vertex other than these 2 vertex, am I right? The same. But what's the thing we forget?
Divided by 2.
Okay, that's it for today. Bye-bye.
Hello!
Hello, Mr. Eric, Mr. Ryan, are you right?
Yes.
Okay, so we're given this undirected graph. We want to find the number of unreachable pairs, right? Unreachable pairs. And we talk about the depth of search, we talk about the breadth of search, and today we're going to talk about using this union find data structure, union find, to solve this problem. By using union find algorithm, we also need to mention this disjoint set. Okay, disjoint set data structure. We have talked about this before. So we are given an undirected graph. We want to find out the number of unreachable pairs. 1, 2, 3, 4, 5. The unreachable pairs is 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5. Right? So 1, 3 is the same as 3, 1, so we don't count these duplicative pairs, okay? Previously, we're using the depth of search and breadth of search to solve this problem. The idea is to count the number of the vertex in a connected component. So the answer, for example, given this undirected graph is 2 times 5 minus 2 plus 3 times 5 minus 3 divided by 2. So there are 5 vertex total. So 2 times 5 minus 2 means that we have 2 vertex here, and then 5 minus 2 is the number of vertex other than these 2 vertex. Right? So it means that, look, for each vertex in this connected group, we can form an unreachable pairs by connecting this vertex to all other vertex. And same goes with this 3 times 5 minus 3 here. So, but we add it together, we need to divide it by 2 because that 1, 3 and 3, 1, we count it twice, we need to divide it by 2. Right? That we're using the depth search, breadth search. Basically, we just want to calculate this sum, c times n minus c divided by 2. C, the number of vertex in each connected component, and n is the number of all the vertex in this undirected graph. Today, we're going to use disjoint set data structure. We want to find out the number of vertex in this connected component using this disjoint set and union finding. So disjoint set, when we talk about disjoint set, is the data structure. When we talk about union find, is the algorithm. Okay, so but all of these, depth search, breadth search, and this union find, basically wants to solve this problem by computing the c and n minus c, the sum of it, right? The main task is to find out the number of the vertex in the connected component. If the undirected graph is one single piece of component, then the number of unreachable pairs is 0. So everything is connected, so it does not have any unreachable pairs to other vertex. Disjoint means that non-overlapping. So at the beginning, we have n vertex. Each one has its own group, its own set, right? So this 0, 1, 2, 3, 4. If there's an edge between 0 to 1, for example, 0 to 1, we just merge these two sets. At the end, we just need to get the number of vertex, number of elements in each set. Okay, so this answer the number of unreachable pairs. Then we can go through these edges. Disjoint set dot merge A, B. Okay, this disjoint set at the beginning, we create a disjoint set with the n vertex. Then we need to sum these. Okay, for I in range n, C equals ds dot get size. We want to get the number of elements in vertex I, and then answer plus equals c times n minus c. And at the end, we need to return divided by 2. Or answer shifted one position to the right. The key thing here is that we need to implement this. We need to get the number of vertex in the group of I. The advantage of using this disjoint set is that it provides the near constant time in the operation of add a new set, merge two sets, and find if an element in a set. In order to achieve the near constant time, we need to compress the path. So for example, like 0, 1, 2, 3, 4, 5, right? If we don't compress the path, every time we merge, let's say merge 0 to 1, 0 to 1, okay? And then if we merge 1 to 2, okay? If we merge 2 to 3, etc. If we don't compress the path, it's like a linked list. And in order to find the root of 0, it needs to take O(n) time. So that's very inefficient. So we have to compress the path. So when we find the root, we can reassign the root. We can compress the path. So we can store the number of the sizes. We can store the sizes for the group, or we can store the rank. Okay. So rank is like the upper bound of the height. The size will be more straightforward. So let's use this size. Size, for example, like if we have a element here, right? So we have these. This is size 1, 2, 3, 4, and then if we have another 2 here, so it's better to merge the smaller size into the bigger one, rather than from the bigger one into the smaller one. Class disjoint set. Object define init. Init is the constructor. Self and so self dot parent at the beginning. The parent is the from 0 to n minus 1. So we give it a list range. Range n is from 0 to n minus 1. So the parent will be from 0 to n minus 1. And the size it will be at the beginning will be all 1. At the beginning, each number is assigned to its own group, own set. Self dot total component, so total size equals at the beginning n. So this is useful if we successfully merge two components. We can decrement this total. Merge we want to merge A and B. Right? So at the beginning we need to find A and B equals find, self-define, okay? Self-define A, self-define B, okay? Then if A equal B, if the parent is the same, if they already belong to the same group, then we just return false. There's no need to continue. Now we just need to find the size. If the size, okay, say of the size A is smaller than say of the size B, then let's swap it, okay? AB equals BA. This is the way to swap these two variables. So at this point, the size of A is bigger than size of B, equal or more than size of B. And then we can reattach B to A. So self dot parent B equals A. Then self the size of A needs to plus equals self the size B, right? So because look, this is the size of A, this is the size of B, and we want to merge this B into A, right? So the size of A has been incremented by the size of B, but at the same time we need to set the size of B equals to nothing. B equals 0, right? So we can use this size function later. This is very important. And return true. Okay, and then we need to implement this find function. This find function, we use the iterated or recursion. So the recursion will be very easy to implement. Define find self A. Okay, so with the recursion, we just have to check if A is not equal to self dot parent of A, self dot parent A equals self dot find self dot parent A. Okay, so this is recursion. If A is not the root, right? If A is not in the root, we might go up to the path, right? If we haven't reached the root yet, this is to compress the path. We need to compress the path, and this is recursion to find its root. At the end, we just return self dot parent A. If a path is like that, we want to find the root of these. So at the end, these will be pointing to here, and these will be pointing to here. It will become a balanced structure. So the total cost of tracing the root will be minimized. If it's like a linked list, then finding the root of this needs to take O(n) time. By rearranging the parents, we can minimize the cost. So this is recursion. We can also use the non-recursive method. At the beginning, we need to find the root. Okay, root equals A, while root not equals self dot parent root. This is iteratively. Then root equals self dot parent root. Now we get the root, and then we need to traverse the x again. X equals A, why x not equals self dot parent x. Right? Then we need to find out the parent of it. So px equals self dot parent x. And now self dot parent x. Now we need to reassign these to root, right? Equals root. And then x equals px, okay? And return root, right? Because with this function returns the root, we just need to find the root parent of the A. And then this is to compress the path. So that union find, right? So union, this is find. And this, the whole thing is the disjoint set. Based on these, we can calculate the number of sizes for each component. Define get size, self A. Now we just return self dot size A. Okay, property. Okay, define count, and then self. We can just return self dot total. But when we merge it, so because we said when we merge it, we need to decrement this. Right? So before this the return true, we need to say self dot total minus equals 1. Because every time we merge two components, the total number of components should be decremented by 1. What's the problem and what have you learned today?
The problem is we have this nodes.
Yeah, we are given this
Undirected.
undirected graph, and what's the task we're going to solve?
Find the number of unreachable nodes.
Yeah, unreachable pairs. Okay, so given this, there are three components. Yeah, this is undirected graph. The one, there's edge here, there's two edge. So how do we calculate the number of the unreachable pairs?
So the number of like connected things.
Yeah.
There's a connected thing apart times the number of nodes in the other parts.
Yes. For example, given this, there are 6 nodes, right? So the number of unreachable pairs is what?
Like this. So you times
1. That's 1 node here. Times what?
Times 5. 6.
5.
6 minus 1.
Yeah. Okay. Plus. Okay. How about this one?
2
Times
6 minus 2.
plus.
3 times 6 minus 3.
Okay. And
Divided by 2.
yeah, divided by 2. All together divided by 2. Okay. We know the total number is 6 nodes. 6 minus 1 is all other vertex not in this connected component. And similarly, etc. And we add it all together. We need to divide it by 2 because any pairs are counted twice. That's why we need to divide it by 2. And previously, we're using the depth search, breadth search, traverse the vertex in the component disjoint set, non-overlapping set. So we can use this data structure to find the number of vertex in one component, and that serves the purpose. So we just have to count the sum of c times n minus c divided by 2. C is the number of vertex in each component. Okay, that's it. Bye bye.
Bye.